Hi everyone, I'm Dongjin. I'm presenting our work, I'm me, we're us, and I'm us, Tri-directional Contrastive Learning on Hypergraphs. Hypergraphs are everywhere. In the real world, many types of interactions are group-wise. Collaborations of researchers and joint interactions of proteins are examples of group-wise interactions. A hypergraph can represent such group-wise interactions naturally. A hypergraph is a set of hyperedges that allow containing any number of nodes. Recently, machine learning on hypergraphs has drawn a lot of attention from a broad range of fields, and hypergraph-based machine learning approach show its effectiveness on various tasks. Previous studies have largely focused on developing hypergraph neural network models, and in most cases, such models are trained in a semi-supervised or supervised way. However, high-quality data labeling is time, resource, and labor-intensive, and hypergraph neural networks trained in a supervised way may overfit and fail to generalize, making it difficult to be applied to other tasks. Thus, self-supervised learning, which does not require labels, has become popular, and especially contrastive learning has achieved great success. A common framework of contrastive learning aims to maximize the agreement between differently augmented views of the same input using a contrastive loss. For example, SimClear creates two augmented views from the input and maximizes the agreement between the two views. GRACE is a model similar to SimClear, which can be applied to graph datasets. Contrastive learning has demonstrated its effectiveness in computer vision, NLP, and graph domains. Despite the development of contrastive learning in other domains, contrastive learning on hypergraphs is still in its infancy. In this work, we propose TriCL, a novel hypergraph contrastive learning method, to answer the following questions. First, what to contrast? Second, how to augment a hypergraph? Third, how to select negative samples. Let me introduce TriCL. Our goal is to train a hypergraph encoder in contrastive manner. The encoder produces the node and hyperedge embeddings, and these embeddings may be utilized for downstream tasks such as node classification and clustering. This is the architecture of TriCL. TriCL follows the conventional contrastive learning paradigm where the model tries to maximize the agreement between different views. While the most existing approach only use node-level contrast when the downstream task is node-level. The big difference between TriCL and previous method is that TriCL applies three forms of contrast for each of the three essential elements constituting hypergraphs. There are nodes, hyperedges, and node hyperedge memberships. TriCL is composed of four components. Let's talk about these components one by one. The first component is hypergraph augmentation. Contrastive learning needs two different views of an original hypergraph because it requires something to contrast. So, TriCL first generates two alternative views of the hypergraph by applying stochastic hypergraph augmentation function T1 and T2. We use a combination of random node feature masking and membership masking to augment the hypergraph. Node feature masking and membership masking randomly drop out the node features and the instance matrix by sampling from a Bernoulli distribution with probability p respectively. The instance matrix is a logical matrix that shows the relationship between nodes and hyperedges and is represented by matrix H in the figure. The second component is the hypergraph encoder. A hypergraph encoder produces node and hyperedge representations P and Q for two augmented views. TriCL does not constrain the choice of hypergraph encoder, but in this method, we use a simple min pooling layer as an encoder. The third component is projection head. We use two projection heads for node and hyperedge embeddings respectively. Some research empirically demonstrates that including a projection head helps to improve the quality of representations. Both projection heads are implemented with a two-layer MLP and ELU activation. They produce projected embeddings Z and Y. The last component is Tri-directional Contrastive Lows, which is our main focus. We propose Tri-directional Contrastive Lows, which consist of three forms of contrast. Node-level contrast aims to discriminate the embedding of the same node in the two views from other node embeddings. Group-level contrast aims to discriminate the embedding of the same hyperedge in the two views from other hyperedge embeddings. Membership-level contrast tries to differentiate a real membership from a fake one across the two views. How can the three forms of contrast be helpful for representation learning? In node classification, for example, information about a group of nodes could help improve performance. Specifically, in co-authorship network, node and hyperedges represent papers and authors respectively, and papers written by the same author are more likely to belong to the same field and cover similar topics. We can say that homophily exists in hypergraphs. Thus, high-quality author information could be useful in inferring the field of the papers he wrote, especially when information about the paper is insufficient. Furthermore, leveraging node hyperedge membership helps enrich the information of each node and hyperedge. For example, the fact that a meteorology paper is written by an author who mainly study machine learning is a useful clue to suspect that the paper is about application of machine learning techniques to meteorological problems, and the author is interested in both machine learning and meteorology. Similarly, we can also guess that the author is likely to be interested in economy from the fact that he wrote a paper about the economical problem. In order to utilize such benefits explicitly, we propose the Tri-directional Contrastive Lows. In detail, node contrastive lows aims to discriminate the same node from other nodes and embed microscopic structural information into embeddings. This is the loss function of node contrastive lows. And group contrastive lows aims to discriminate the same hyperedge from other hyperedges and embed group-level structural information into embeddings. Membership contrastive lows aims to discriminate a real membership from a fake one, making it apply group-level constraint to nodes. Our proposed tri-directional contrastive lows can be defined as a weighted sum of these three forms of contrastive lows. We assess the performance of TriCL on 10 commonly used benchmark datasets. The datasets are collected from real-world networks from different domains. We include a broad range of methods as baselines, including 10 supervised and 4 unsupervised models. Note that to evaluate the graph-based method on hypergraph datasets, we employ the graph-based methods after transforming hypergraphs to graphs via click expansion. To evaluate the node embeddings, we use linear evaluation protocol for the node classification task and K-means clustering for the clustering task. These are the commonly used evaluation protocol for assessing the unsupervised learning methods. In details, each hypergraph encoder is firstly trained in a fully unsupervised manner, and then a simple logistic regression model is trained on top of the frozen embeddings without flowing any gradient back to the hypergraph encoder. K-means clustering is also employed on the top of the frozen embeddings. This table summarizes the node classification performance of all methods. Overall, TriCL achieves the strongest performance across all datasets. TriCL consistently outperforms its unsupervised baselines by significant margins, and surprisingly, it also outperforms the models trained with label supervision. Here, TriCL-N and TriCL-NG are variants of TriCL, which use only node contrast and node and group contrast respectively. To validate the effect of each type of contrast, we conducted an ablation study. In this table, we note that the more types of contrast we use, the better the performance tends to be. Using all types of contrast achieves the best performance in most cases, as they are complementarily reinforcing each other. To analyze how the number of negative samples influences the node classification performance, we propose an approximation of TriCL's objectives called TriCL subsampling. Here, instead of constructing the contrastive loss with all negatives, we randomly subsample K negatives across the hypergraph for node and group contrast respectively at every gradient step. Our research showed that TriCL is very robust to the number of negatives. Even if only 2 negative samples are used for node and group level contrast, the performance degradation is less than 1%. And it still outperforms the best performing unsupervised baseline method. The results indicate that the random negative sampling is sufficiently effective for TriCL, and there is no need to select hard negatives, which incur additional cost. Next, to show how well node embeddings trained with TriCL generalize across various downstream tasks, we evaluate the representation on the clustering task by k-means. As seen in this table, TriCL achieves strong clustering performance in terms of all metrics across all datasets. This is because the node embeddings learned by TriCL simultaneously preserve local and community structural information by fully utilizing group-level contrast. We use TSNE plots of the node embeddings produced by TriCL and its 2 variants to represent the quality of embeddings intuitively. As expected from the previous results, the TSNE plots of TriCL show more visually and numerically distinguishable clusters than its 2 variants. So we can say that all types of contrast are helpful. In conclusion, we propose TriCL, a novel hypergraph contrastive learning method. To answer question 1, we propose tridirectional contrast, which is a combination of node, group, and membership contrast. And we demonstrate that using all types of contrast improves the quality of the learned embeddings. For the second question, we use node feature masking and membership masking as hypergraph augmentation and showed their effectiveness. For the last question, we showed that a uniform random negative sampling is effective and TriCL is very robust to the number of negatives. The code and datasets using this work are provided at this URL. Feel free to ask a question about the code and datasets. Thank you very much for attending our presentation.